In this lecture, I'm gonna be talking about how we can use contrastive learning and few-shot learning. How can we leverage these two paradigms to enhance state-of-the-art NER, name entity recognition? And the name of this model that they have designed is called container. So I will be talking about this paper in 2022, which is called Few-Shot Name Entity Recognition via Contrastive Learning. And this is a positive sample. Name entity recognition in few-shot setting is imperative for entity tagging in low-resource domains. Existing approaches only learns class-specific semantic features and intermediate representations from source domains. This affects generalizability to unseen target domains, resulting in suboptimal performances. To this end, they present this model container, which is a novel contrastive learning technique that optimizes the inter-token distribution distance for few-shot name entity recognition. Instead of optimizing class-specific attributes, container optimizes the generalized objective of differentiating between token categories based on their Gaussian distributed embeddings. So, for example, this island, this has an attraction with this Christ Church. So some tokens have attraction, some of them have repulsion. So we can get this idea. It's just single sentence, and we want to take advantage of this idea. And in the context of few-shot learning, when we have n tokens, we have a sequence of n tokens x1 through xn. First, we create our support and query set. For example, this tag set, and we have source domain, we have target domain. And you are familiar with domain adaptation and everything in transfer learning, because it's a real issues, because our data has scarcity. So because our target data is our test data set, so it's a scarce, is a data scarce target domain. And the tag set are for the target. So we separate this source with the target. But still we are in the context of few-shot learning. We have n-way k-shot. K-shot means k examples. N-way means k classes, n classes. So we have n classes, for example, class location, for example, person. But we have, for each of them, we have k different examples for each of these classes or ways. So the tagging scheme for fair comparison of container against previous models, we follow this IO tagging scheme, where I type represents all of the tokens that are inside. I stands for inside, and O is other. O stands for other. So this is the architecture. As I said, some tokens repel each other, some of them attract each other. But we have some very scarce target domain and some relatively big source domain. And we want to move from source to target, source domain to target, and transfer all we have learned. We don't want to forget what we have learned. It's not like continual learning, but it has some similarities. We are talking about transfer learning, but the way that we do domain adaptation is different. Then we go to nearest neighbor inference and we do the inference. But we have this pre-trained language model. We can use any pre-trained language model that you have. And then you give it to projection network. So this container model, the introduced container model, utilizes contrastive learning to optimize distributional divergence between different token entity representation. Instead of focusing on label-specific attributes, this contradistinction explicitly trains the model to distinguish between different categories of tokens. Furthermore, modeling Gaussian embedding instead of traditional point representation effectively lets container model the entity class distribution, which incites generalized representations of token. So we first train our model in the source domain, then we fine-tune. So fine-tuning is in the target. So we fine-tune the model using few sample support set, because we have just few samples, to adapt it to a target domain. And the training and fine-tuning is showed in the algorithm 1. But first we have a sequence of n tokens and we give it to this pre-trained language model to have a good representations. As you see, for each token we have a representation. So we have n tokens and representations. I've explained SimCLR in a different video. So unlike SimCLR that uses projected, we had a projection layer. For contrastive learning, we assume that token embeddings follow Gaussian distributions. So here, the token embeddings, they are Gaussian distributions, and so specifically, we employ projection network F mu because it's the mean, and F sigma for the variance. So mu I and sigma I represents mean and diagonal covariance of the Gaussian embedding. So our projection is not a deep layer. It is a deep layer, but it's not like the one that we create in SimCLR, very traditional approach. What we are learning is different. We are learning the mean and the variance. We are learning the mean and variance, and for calculating the contrastive loss, we consider the KL divergence between all valid token pairs in the sample batch. Two tokens, X sub P and X sub Q, are considered as positive examples if they have the same label. So, given their Gaussian embeddings, we can calculate their KL divergences. Remember, SimCLR, we had, for example, we had image, then we have to augmentation, then we have representation, then we give it to projection. If you remember this projection. So what we are doing is, instead of this, we just model the mean and the variance of that. Do you know why? Because as this is more elaborate, and we can do KL divergence between the two positive pairs very easily, because it is explicit and it has some advantages. Because we are talking about the distributions, and both directions of the KL divergence are calculated, since it is not symmetric. So we are symmetrizing the KL. As you know, KL divergence is not symmetric, so we try to symmetrize it by just the opposite way, and then like the technique that we use every time, even in the loss of BYOL, they symmetrize their loss, although their architecture is asymmetric. So we first train our model in resource-rich source domain, having training data, and at each training step, we randomly sample a batch of sequences from the training set having batch set size of B. And then we obtain its Gaussian embeddings by channeling the corresponding token sequence through the model. We find in batch positive samples and subsequently calculate the Gaussian embedding loss with respect to all other valid tokens in the batch. Those have the same label. Those pairs that have the same label. I mean, they're XQ and YQ. For example, two tokens. And in this way, we can calculate the distributional divergence of all token pairs in the batch. So the sum is over all tokens pair in the batch. We do not scale the contrastive loss by any normalization factor, since we did not find it to be beneficial. So they experimentally understood that it is not beneficial for them. So, and then we fine-tune to target domain using the support set. But they use early stopping. Fine-tuning with a small support set runs the risk of overfitting. And it's just one of several techniques that you can avoid early stopping. So fine-tuning with a small support runs the risk of overfitting. We have very few samples, few shots. So it has the risk of naturally overfitting, which is terrible. This action is terrible. So we should early stop the algorithm from learning. So we rely on the calculated contrastive loss and use it as an early stopping criteria. Because this calculated contrastive loss is unbiased, it's based on something that is meaningful, and so it prevents from this overfitting. So the algorithm, we need the training data, support data, train loss. You need to pick a pre-trained language model. Just look at Hugging Face. Just pick one of those already pre-trained models. And then for sample or without replacement, of course, with mini batch X, we first calculate the mean and variance, because the pre-trained language model gives you something, but then your projection of mean and also for the variance, you are learning those things in order to calculate the loss, because that KLA divergence needs those equations 5 and 4. And then finally, the loss over all of these pairs, not just one. After that, we are going to the target domain and fine-tuning to the target domain. So after training and fine-tuning the network with train and support respectively, we extract pre-trained language model encoder for inference. Similar to SimCLR, we found that representations before the projection layer actually contain more information than the final output representation, which contributes to better performances. So F mu and F sigma projection heads are not used for inference. We thus calculate the representation of the test data from the pre-trained language model and find nearest neighbor support set representation for inference. And the PLM representation of each of the support token can be calculated as I've shown you before, but similarly for test data, we get the pre-trained language model representation and we assign the same label as the support that is nearest in the pre-trained language model representation space. We just take the minimum of that. Of course, we should use Viterbi decoding because most previous works notice performance improvement by using CRF, which removes false predictions to improve performance. Thus, we also employ Viterbi decoding in the inference stage with an abstract transition distribution as in structure. For the transition probabilities, the transition between three abstract tags, outer, inside, outer, is estimated by the counter by counting their occurrences in the trains. And the emission probabilities, if you have seen my playlist for Markov chain, my playlist for CRF, then you are familiar with all of these transition probabilities and emission probabilities. Comparing domain transfer results, we find that interestingly, if there is no significant domain shift involved in test data, contrastive learning allows container to automatically extract label dependencies, obviating the requirement of extra Viterbi decoding stage. So in this experiment, a model trained on a source domain is deployed to previously unseen novel text domain. Here we use unknowns, which people use for few-shot learning. Also, I2B2, we should register for that. If your institution is not substituted, registered to Harvard, then you should do it as a personal, private thing. It's faster. They reply to you very fast. And there are other data sets that we can use. So if you have 5-shot, then you expect that you have a better accuracy and F1 score. Here is a F1 score. And F1 score in the domain extension as the source domain. So results vary slightly comparing to this reference, since they used different support set samples than this paper.